welcome to Classical Mechanics 2. In this video, we'll learn how to model dynamical systems. This is one of my favorite topics that we cover in this course. It's a topic that you don't see in most physics classes, but it builds off of the same type of quantitative thinking we've been developing thus far to explain many phenomena in the real world. In this video, we'll in detail go through the predator-prey model, which is a simple model for ecology. Sometimes this is called the Lotka-Volterra or logistics growth model. It looks like the interactions between the population of predators and the population of a prey species. Imagine a lush green meadow, and here's a little bunny. She's hopping along, eating some grass, living her best bunny life, and in hops another bunny, and pretty soon, well, sparks fly, and before you know it, there's a bunch of baby bunnies. So let's start by analyzing this single population model. The first thing we observe is that the rate of change of this population is proportional to the size of its population. So that means that the first generation we start with 2 bunnies, and we end up with 3 bunnies. Then each pair will go on to produce 3 more bunnies, and so on. We also find that when animals have more food to eat, they produce more offspring. So their reproduction rate is also proportionate to the amount of food they have to eat. So in this mock ecosystem, we assume that rabbits always have enough food to eat. If the population is A, then a differential equation for its growth says that dA by dt is equal to C times A. Thus, this gives us exponential growth for the population of rabbits. At this rate, after 25 generations, the population of rabbits would have the same biomass as all of humanity, and after 35 generations will exceed the biomass of all kingdoms of life on the planet. This would obviously be disastrous for the ecosystem. And in reality, the rabbits or bacteria or any population undergoing exponential growth will end up consuming all available energy sources, and that will limit the population. However, the topic of today is interacting systems. So in our ideal ecosystem, we also introduce a population of foxes. The foxes eat the rabbits, and then they produce more foxes. In this model, the foxes can only eat rabbits, so the rate of change of their population is proportionate to the population of rabbits. And lastly, we assume there's no evolution of the 2 species, and there are no environmental changes to the amount of grass and so on. Let's put this into math now. In the absence of foxes, rabbits have a natural birth rate, BR, and a natural death rate, DR. Both of these depend on the size of the population of rabbits. Thus, we can see that this is going to lead to exponential growth or decay, as we just saw. Now let's add in the interaction and have a look at the fox population. So there's some natural rate at which foxes get old and die, so we're going to call that DF. But their growth rate depends on how much they have to eat. That means their growth rate is proportionate to the population of rabbits, R, and there's also a scalar coefficient out front that measures the efficiency of turning rabbits into foxes, so that's going to be BF. In our model, this is the rate at which foxes are happily eating rabbits and reproducing. So we need to subtract that term from the rabbit population. Here's the rate at which rabbits are being eaten, K, times the fox population, F, and it's proportionate to the rabbit population, R. That means that the rabbit population will decline based on how many foxes there are and how many rabbits those foxes need to eat to survive. We can write this a little bit more simply as a set of nonlinear coupled differential equations. So the rate of change of the rabbit population is proportionate to their combined birth and death rates, which we have combined into a single coefficient, so that's A, minus the rate at which rabbits are eaten by foxes times the fox population times the rabbit population. Likewise, the rate of change of the fox population is proportionate to the birth rate of foxes times the population of rabbits times the population of foxes, and the foxes are going to die off at some rate D. Here are 4 solutions to this predator-prey model for different values of the 4 coefficients, A, B, C, and D. These are called phase portraits. The prey population here is on the x-axis, and the predator population is on the y-axis. Each of these 4 cases has different behavior. We'll start out with A equals 1, which is the rate of exponential growth of the rabbit population. B equals 0 means that no rabbits are eaten by foxes. C equals 0 means that there are no foxes being born. D equals 1 is the death rate of foxes. Basically, I've decoupled the two populations in this example. Rabbits aren't being eaten, which means their population is going to grow exponentially. At every point in this plot, the rate of change of the rabbit population and the fox population acts as a vector. So at the point 2, 1.5, the rate of change of the rabbit population is going to be 2, and the rate of change of the fox population is going to be minus 1.5. So the vector 2 minus 1.5 is the rate of change of the populations. If you take an infinitesimal step in the direction of this vector, you'll get a new vector, and basically the dynamics flow along the direction as you move along those vectors, and that allows you to integrate the dynamics. Likewise, each point on this plot represents an initial condition. So this plot can give the dynamics of the whole ensemble of systems just by integrating along streamlines. This is another initial condition, and these are the dynamics of this population. This is a somewhat unphysical system because as the rabbits are growing exponentially, the foxes are not reproducing and they're dying off exponentially. So let's look at two extreme cases next, both of which are also unphysical. The first is what if the rabbits breed and die at the same rate, A equals 0? So that is, their population stays constant, but they're still being eaten by some population of foxes that, in this case, don't die, so that's D equals 0. Here we have a linear decrease in the rabbit population and a linear increase in the fox population. So that gives us straight lines in this phase portrait plot. What about the other extreme case? Here we have a rabbit population that grows exponentially, but is not killed off by foxes. Foxes are breeding at a rate which is proportionate to the population of rabbits. So this would model a different type of ecology, where the foxes rely on something that the rabbits produce, but that does not harm the population of rabbits. The unphysical part of this model is that there is no natural death rate for the foxes. Since the rabbits behave as if they were an isolated system, we know that they're going to have exponential growth. The rate of change of the fox population is proportionate to that exponential growth times the current size of the fox population, which means that it grows faster than exponentially, leading to these sort of curves in our phase portrait. If the foxes also produce something that the rabbits needed, this would be a model of mutualism, although we would need to put a cap on other raw resources available to both the rabbits and the foxes to prevent unbounded exponential growth. This last case shows off a more realistic set of dynamics for this interacting system. Here we have non-zero birth and death rates for the rabbits. They're eaten by foxes, and the foxes reproduce at some rate. And the foxes also die off at some rate. So we've set all of these dynamics equal to 1, but these numbers in reality must come from the specific ecosystem you're studying. Let's take an initial condition where there are twice as many prey animals as predators. Let's say 2,000 rabbits and 1,000 foxes. The foxes start preying on rabbits a bit faster than the rabbit reproduction rate can keep up. So the fox population is going to start to grow, so it's motion in this direction, but the rabbit population is going to decrease, so that's in this direction. So it starts to move like this. At some point, eventually, there will be too few rabbits to sustain the fox population. So the fox population is going to collapse, but without foxes to eat the rabbit population is going to start to explode, and with it, the fox population is going to start to grow. And this dynamics is going to continue cyclically. Basically, there's a phase lag between the growth and crash of each of these populations. There are several other famous models of interacting systems that can be analyzed using similar methods. One of them is an autocatalytic chemical reaction known as the BZ reaction. Another you've likely heard of more than you'd like in the last few years is the SIR model of epidemiology. In the next video, we'll look at a few different numeric techniques to solve this type of differential equations. Thanks for watching, and I'll see you next time.